Well, looks like we can start. Welcome back. We're now in week 15, so the penultimate week of the entire semester. And we finished the course content last Thursday that we had class. So the plan for today is just reviewing entirely for the final exam. So I sent out another round of emails through Canvas to everyone for scheduling the final exam. If you already scheduled yours, then you can just disregard that email. And sorry to the people on the Idaho Falls campus, I had to send a message twice since I accidentally sent the first link incorrectly. So I had to send the second link as well. But just a quick reminder for how the final exam is going to work. The math department requires it be taken either after 2 p.m. on Monday or anytime the testing center is open on Tuesday. So just those two specific days. It's a comprehensive exam, but no section is emphasized more than any other. It's a pretty smooth or pretty even coverage for the entire course, all the way to the last section, 11.1. And the thing we were alerted just last Thursday of last week, a little late, but we were alerted that for this particular exam, the math department is allowing a 4-inch by 6-inch note card, both sides. So that gives us a lot of good real estate to put on formulas, say quadratic formulas, methods maybe like completing the square. They say it cannot contain examples of problems. So it can't be, say, like a problem and the full solution, but just more formulas, definitions, ideas is what goes on the note card. And it has to be collected after the final exam. So that's pretty much what we have going on for the final exam. Any questions at all before the next bit of the announcements? Okay, as far as reviewing for the final exam, the last quiz is going to be quiz number 12. And the sooner you get that in for everyone in the class, the faster I'll try to grade it and get it back to you as promptly as possible. So it can be an extra resource to help study. Also, on this part right here, I mentioned there's a final due date for turning in quizzes. I don't have a late policy on quizzes, so even if, say, you missed quiz 2, but you just want to get that in and turned in, I'll accept it for credit. The last day to get it turned in is going to be Monday, December 15th. And it's also the last day to work in the Newton system to improve your grade. So Monday's kind of like the last day for everything except the final exam can be scheduled on Tuesday if you prefer. That works better with your schedule. So getting caught up on Newton, getting caught up in quizzes is a great way to start studying. Then I have 3 different versions of a sample final exam problems listed down here. There's another version split into 2 parts that you can see in the Newton homework system. And we'll be going over this one this week, this other sample final exam. So this will be the document that we'll be working and updating as we solve through these problems. So pretty much that's our goal this week, solve as many problems on this document as possible. If for some reason I don't get to the very last problem, I'll still come back here, make sure every problem is solved, and have them uploaded sometime on Friday, probably early on Friday. Well, any last questions at all before we jump in? Okay, well, let's take a look into this sample final exam. This was written by the math department. And the final exam itself is also written by the math department. They decided on all the policies, like the no card policies and so on. But I've had a chance to look into the real final exam, as well as this sample that we're looking into right here, and they're pretty close. This one's kind of a longer exam because it's meant to help with the review. But the kind of questions that you can expect to see on the real final exam are pretty similar to the ones that we're going to be solving here on this review set of notes. So the first page is pretty similar as well. You'll have 2 hours for the final exam. You have to show work, simplify answers, box circle your answers. I would say I'm not too critical about that unless, say, the work kind of gets really busy. It's hard to tell where everything is. Then that's a good idea. Scientific calculators allowed. A basic calculator will work, so it'll be up to you to know to make sure you have a scientific calculator in the testing center. Problems 1 through 19 are graded on a no partial credit basis, worth 2 to 4 points each. They're usually fast concept questions. Problems 20 to 32 are eligible for partial credit, and these are the longer questions at the very end. There's 100 points in total, and we're told here the actual final exam has 3 fewer questions. So this one's just a little bit longer. Well, let's give this a start. It says graph the horizontal line through the ordered pair negative 2, 3. And then after graphing it, write the equation of the horizontal line. This is something I believe we did on exam 1. For as far as graphing the equation, first you'd want to go to the point -2, 3, which is here. When it was saying horizontal, that means it has to go through like this. So first part is done. Even though there's no partial credit, really this part would be 1 point. And if I mess up the equation, I would still get one of the 2 points. So it's not as harsh as it sounds when it says no partial credit. It's just that this part right here is really all or nothing. So we graph the equation. When it says write the equation of the horizontal line, the equation is going to be y equals 3. So horizontal means we go to the second coordinate, draw a flat line horizontal, and you use y equals that particular number for the equation itself. Well, we did it. That's the horizontal line. You know, because it's an exam review, let's change this up a little bit. Let's suppose the instruction said, let's call this problem 1, second version. Graph the equation of the vertical line that goes through to -2, 3. Then write the equation of the vertical line. So it can be any version on the final exam. I think these are pretty much just randomly selected using a random number generator. But assuming the problem said vertical line, here's how the work would differ on this version. I'll have to hand draw in the graph paper here. So here's the point -2, 3 once again. Vertical means the line now goes this way. Supposed to go cleanly through that tick mark, but we'll use our imagination for that. It does go through the point -2, 3, but it's going through vertically. And for the equation of the line, that would just be x equals -2. So as far as vertical lines go, we use the point x coordinate -2 and just go vertically through the x-axis. And the equation has to be written as x equals. So horizontal is connected with the y equals part, and vertical is connected with the x equals part. And that's 1 out of 32. We have 31 left to go. Any questions at the moment? Okay, you might notice as you go to problem 2, the exam is a little bit scrambled. This will be true of the final exam. Some of the stuff is just a little bit out of order. Some of it seems to go in about the order the course went. It's as if someone put in a scrambler, but they didn't try to scramble it thoroughly, just a little bit mixed up here and there. For the next one, it says rationalize the denominator, simplify if possible. And by rationalizing the denominator, what we mean is we don't want any root, not that square root we see there, in a denominator whatsoever. So here's one way to work through this problem. We have root 15 divided by root 35. Now, if we multiply up top and bottom by the square root of 35, we would remove the square root from the denominator, but we still have to simplify what we get, and we'd have a pretty bigger number, 35 times 15, inside this root. That's not a bad way to go, but I think it takes a little bit more extra steps. But notice if you do this, if you use a property of square roots, and put this under one big root, excuse me, it simplifies on the inside. You can divide, let's see, the numerator by 5, the denominator by 5. Had to do a quick micro sleep there to think about that. 5 goes in here 3 times. in the denominator 7 times. Then if you broke this up as root 3 over root 7, it's just a faster looking problem. There's less noise here. The numbers are smaller, more contained. Here's where we'll actually rationalize the denominator. We have to eliminate the fact that there's a square root 7 in the denominator. So we multiply by root 7 over root 7. In the denominator, root 7 times root 7 just comes out as a 7. In the numerator, we can combine the two roots and get root 3 times 7 for 21. But that root in the numerator doesn't simplify, and this is the end answer on this one. So pretty fast question so far, and then no partial credit section. This is about what they look like going down the list. Usually they're more kind of a concepts type of question, like problem number 3 below. Well, before we go to problem number 3, this one's talking about the discriminant of a quadratic function. We're told it's 81, and we could check that, but you know, it's okay to just trust them on the exam. I believe it's probably 81 if they said so. Then it goes on to say, therefore the quadratic equation has A through E different possibilities. Well, this one's just multiple choice, so it's a really fast concept question. It's worth just 1 point on the exam. Let's think about what we know for sure about this. Can't be infinitely many solutions. One equation with degree 2 means at most 2 equations, but there can't even be 3 on this one. So this one's out. Now it's between no solutions, 2, 1, or 2 solutions. But you know, as far as quadratic equations go, they always have a solution. Sometimes those solutions are complex valued, but that eliminates part A. There will be a solution to this, possibly 1, but more likely 2. And again, it's just a concept question. Let's put this in the notes in case you decide to come back here to take a look. This is a quadratic formula kind of question. And the big thing about using the quadratic formula was we often mentioned the discriminant tells you the nature and the number of solutions. So when it's positive, there's 2 real number solutions. 0 means exactly 1 unique solution. And negative means 2 complex number solutions. Let's put this in context of the problem that we're actually solving as a reminder. Okay, close that. And it tells us the answer to this one is B, 2 distinct real solutions, because the discriminant is 81, which matches the bigger than 0 part here for 2 real number solutions. Well, that one's one you could take some time thinking about, but if we know what's going on with the discriminant, probably good information for a note card. This one is a really fast 1 point to move through. Next one is factoring using AC method for factoring. Now, as far as this question goes, I don't know if AC method is everyone's favorite method. Some people in this class used it a lot. Other people seem to avoid it like the plague. It seems like people almost have like a tribal mentality when it comes to factoring trinomials. Some people like a specific method and really hate all others. Some people are okay with either method. It says use the AC method to factor, which might indicate it's a pretty good method for this problem. But if you factored it using trial and error, I wouldn't think that's a big deal. So if you pick any method that works correctly, that's what matters most to me on this one. But because it said the AC method, let's review how that goes and give it a try. First, with the AC method, let me copy it down again here. 6x squared plus 5x minus 14. The first thing we do is we take these numbers, 6 and negative 14, and multiply them together. So 6 by negative 14 gives us that 60, 24. That's equal to negative 84. Next thing we do is we take this number and just copy it in. So you multiply the A and the C. This is why it's called the AC method, even though we use the B coefficient as well. AC method means multiply those together, then copy the coefficient b down here. Once we have that down, we're now solving two different equations. One's a multiplication equation, the first row right here. The second equation is an addition equation using the same values we found above for the multiplication equation. So if we can find two numbers that multiply to -84, add back to 5, then we can rewrite the middle term here, which is +5, using those two numbers. So this is the gist of the so-called AC method. It's not my favorite method because sometimes I look at this and I see what feels like lots and lots of possibilities. It's hard to know where to start. But this is the way I usually get through it. It's kind of like dealing with square roots or cube roots and so on in chapter 8. If you factor 84, it just reveals all the secrets. The smallest prime factor divides as 2, going in 42 times. 2 goes into 42 21 times. Next prime factor is 3, which goes into 21 7 times. And this is the full prime factorization. Then we need two numbers adding to 5. So one of them's positive, one's negative, because they multiply to -84. But you know, if you took 2 times 2 times 3, that's 12. Times 7 gets you to 84. And the difference between those two numbers is 5 exactly. So it looks like 12 and 4 is what we need here. We just have to decide which one's the positive. Probably the 12. We can go 12 plus a -5. And let me try again. Let's go 12 plus a -7, and then that will bounce to 5. 12 times -7, based on our factor tree on the right, multiplies to -84. And so we're ready to start the AC method. The AC method kind of eliminates trial and error, but only by a little bit. There's still some trial and error in just finding the right combination here to solve both equations. But once we have that down, the rest of it is pretty smooth. This is the nice part of the AC method. We can rewrite as 6x squared. The positive 5x that we had, we can transition this to a plus 12x minus a 7x, and then minus 14. So with all that put together, the idea now with the AC method is the first two terms will factor, and so will the last two terms. So for the first two, we can factor out, say, how about, let's see, looking at a 6x squared. Let's factor out, say, just a 6x there. On the last two terms, well, we can factor out, say, a 7, or maybe a -7. Let's go for a -7 on the last two. So if we factor out a 6x from the first two, what we're left with is divide 6x here, and we get just an x. Divide 6x here, and we'll get a +2. Then factor out a -7, so we'll write in a -7 next. Like before, factoring greatest common factors, just fancy division. Divide by -7 here, we get an x. Divide by -7 here, and we get a +2. And by the work so far, because we've duplicated an x plus 2, both here and here, this tells us the method is working. We didn't make any mistakes. The equations were solved right. The factoring steps worked right. Because now we have a new greatest common factor. It's x plus 2. And if we factor out x plus 2 to the left, here's what we're left with. X plus 2 multiplying just a 6x minus 7. And that's finally the full factorization. Again, I think I would have came up with that faster if I just used ordinary trial and error, but this just depends on the individual. Some people find this is the most streamlined and direct way to do it, and they'll probably solve it this way faster. Well, I'll leave it up to you how you decide to solve it on the final exam. But any questions on getting through that one? Okay, let's see what's coming up next. Looks like it's changing gears a little bit. Here we were just factoring, but on problem number 5, this one involves solving an equation. Let's move example 6 a little bit further down. It says determine the values for which this rational expression is undefined. That's some very specific instructions. When we're checking if something is undefined, this means we are finding the excluded values, which we often abbreviated as E dot V dot, you saw in the notes often in, say, chapter 7. To get the excluded values, or to find out how it's undefined, either way we think about it, it's all about how could the denominator of the fraction come out as 0. Anything divided by 0 is undefined, and so anything that makes the variable x 0 is an excluded value. So whether we call it excluded value or undefined, any way of thinking about it, it's all about taking just the denominator, x squared plus 2x minus 8, and solving this quadratic equation. But we have a lot of tools for solving this. We could factor it using trial and error. I'd say that's a recommended way. We could factor it with the AC method, but this is the one time I would discourage the AC method. AC method only really shines if there's a coefficient other than a positive or negative one by our x squared. That 6 there is what makes trial and error a little bit more difficult and makes AC method a competing way to go. So here, trial and error is by far better than the AC method. And you can even use a quadratic formula. If you're not sure on how this one might factor down, quadratic formula might be the faster way to go. And that would work just fine. If you spot a click and clean factorization, this is by far and away the best approach. X squared can split as x times x. Negative here suggests mixing the signs, positive and negative. A great way to factor 8 is, say, 4 by 2. We can make the positive a 4, the negative a 2, and now if you were to FOIL this out, multiply here to here, you get negative 2x. Here to here is positive 4x, which sums to positive 2x, which was our target. We already know x squared negative 8 works out here. So just those two multiplications tells us that's the right factorization. And once it's factored like this, we're pretty much home free. Here's the middle step that not everyone often writes, but we'll write it down because, this is a review. We're not trying to do them as fast as possible. Because we have both things multiplying and resulting in 0, that means either the first factor is 0 or the second factor is 0. So the degree 2 polynomial equation splits into 2 degree 1 linear equations, and now we can solve this pretty quickly. One excluded value is negative 4. The other excluded value is positive 2. Or said differently, this, which we call rational expression, is just a fancy fraction. Pick a number x and it turns into a real number. Unless you pick negative 4 or positive 2, that puts a 0 in the below in the denominator. It's no longer a real number, so we call it undefined. Well, these kind of problems can be tricky because it's possible to write down a problem with no excluded value whatsoever. So watch out for those. I believe that occurred on, say, exam 3. So let's call this problem 5, version 2. Suppose the whole thing was, say, x minus 8 divided by x squared plus something like a 25. This is problematic. So if we're trying to determine the excluded values on this one, so same instructions, we would take the denominator, x squared plus 25, set it to 0 and solve. You can't factor this any longer. It's totally non-factorable. But you know what's confusing about this class is you can solve it. There's a way to do this. If you kept on going, you would write out x squared equals negative 25. Then you can take the square root. x is equal to positive or negative square root negative 25, and then that simplifies. The square root of negative 1 is a I, so x becomes positive or negative. Let me write it this way. 5 from the root of 25, I for the negative sign inside the square root. But these are not real number solutions. And when it's asking for the values that make the rational expression undefined, the thing that makes this confusing is we're looking for specifically real numbers. These are too complex number solutions. We're thinking about only using real numbers for this particular problem. And so the answer to this one is no excluded values, because there are no real number solutions. Same situation came up with x-intercepts as well. You can solve these equations trying to find an x-intercept. If you get just two complex number solutions, those are not x-intercepts at all. Same idea here. Complex valued numbers like these also cannot be excluded values. We were only ever plugging in real numbers into these fractions in the very first place. Well, this was a confusing question because of the two different versions that can come up. Any questions at all getting through this one? Okay, let's move on to the next one then. Here's where the exam gets a little bit strange in a certain sense. We never had any questions like this on exams 1, 2, or 3, but the final exam is trying to cover a lot of different topics without being too long of an exam in the first place. It's a 2-hour exam, so not every single thing we did in class we can write out in the full details. So some of the problems look like this, set up, but do not solve a system of equations that can determine how much money this person put in each account. I guess this person is Carol. So it's kind of a weird problem. It's just a setup problem. And then we stop once we have the right equations. So let's read through the context. We're told Carol invested $2,560, part at an annual interest rate of 6%, the rest at an 8% rate. So that looks like two quantities, amounts of investments in two different kinds of accounts, a 6% account and an 8% account. We're told overall 7.25% interest was earned after 1 year on her total investment. And we didn't do a lot of actual finances on this kind of thing. We didn't learn a lot of equations for loans, interest, amortizations of loans, and all sorts of things like that. One thing we did learn is the simple interest equation. Simple interest earned in 1 year is given as I, the amount of interest earned, equals P, the principal amount, times R, the interest rate of that account. So that's what we'd be using in this section right here, the simple interest formula. We're only using 1 year, so that's why T isn't present here at all in this formula. And that's similar for pretty much all the equations of this type that we solved in class. So now, this is the major formula we're going to be using. We're going to write down a system of equations. The first thing we need is variables. So to really organize this, let's write out, say, x equals amount invested in the 6% account. Next, for the second amount, y will be equal to the amount invested in the 8% account. And now we're ready to start writing down our equations. There's a couple of interesting objects here. There's the total investment of 2,560 and the fact that she on both accounts earned 7.25% for that total investment when bringing both of the accounts into the picture. So we want to determine how much money she put in each account. We could start off by writing it in x plus y. That's the total amount in each individual account, would be the total investment, $2,560. So system of equations means more than one equation, but we're halfway there. That's one of the two equations. We used that total amount, 2,560. Now there's an interest rate between the two accounts. 7.125% interest was earned after 1 year. So we can write down an equation that gives us that as well. How did she earn that amount of interest? Well, first, this account took into effect after 1 year. Earning 6% means take the principal, that's x, multiply it by the rate, that's the 6%, but we write it in as a 0.06. The percent number has to be in as a decimal, and that's using this equation once. Then we use it again. There's the two accounts, so we go plus, do it again for the 8% account. The principal amount is y. I'll write that in first. The rate for the account y is 8%, so it's 0.08 times y. And we're told finally, after putting these two portions together, this is interest earned. And the interest is at a rate 7.125 between both accounts. So for r here, we put in 0.0725. Again, it has to come in as a decimal number. That's the percent earned on the total amount, the $2,560. So 2,560 would go here. And this simplifies. We could multiply these out if we really wanted to. But you know, right at this step, we have two equations. So that means we wrote up a system of equations. And I would say this is really enough steps. We need the parts to tell us what the variables are, one equation for a total amount, one equation for the total interest earned, and any further steps you took on this is just solving the equation. So this is the point at which we would just stop here. It's as if the person who wrote this exam said, we're going to test on solving systems of equations elsewhere. We're just testing on the concept of transferring these kind of context into the equations. And then don't waste time on solving them, move on to the next problem. Which looks like linear equations again, but any questions at all getting through problem 6? Okay, problem 7 is kind of a roundup of things. It's 3 points, so there's 3 things we're also finding: slope, x, y-intercepts. So really these would all just get 1 point per. So we have a line, 2x plus 5y equals 11. We want both the slope, the x-intercept, and the y-intercept. We're also told we have to write the intercepts as ordered pairs. So we'll navigate that concept as we get through it. But the cool thing about this problem is you get 2 of the 3 just by solving for the y variable, putting it into slope-intercept form. So let's subtract 2x to start this out. 5y is negative 2x plus 11. Then divide all 3 terms by 5, both sides. You'll get y equals negative 2/5 x plus 11/5. This has identified a slope. It has identified a y-intercept. So you could say slope equals, or if you prefer, you can shorten that up, just saying m equals, m is like the international symbol for slope, comes from the French. So m is going to be equal to the negative 2/5. And it has to be specifically that number. We can't include x. Slope is just a constant. Next thing we want is the y-intercept. And we have to write it as ordered pairs, so we need to write this really kind of carefully. The y-intercept means algebraically you put in 0 for x. But look what happens when you put in 0 for x right here. You get negative 2/5 times 0, and all that's left over is the 11/5. That's the reason it's the y-intercept, because of the fact that's what the y-intercept looks like, 0 being placed in for x. Next is the x-intercept. Here we just flip it around. When it comes to x-intercept, the coordinate that goes to 0 is the opposite coordinate, 0. Much like for y-intercept, the coordinate that goes to 0 is the opposite coordinate, x, for y-intercept. But here, if we were plugging in 0 for y, that means this becomes a 0. We're just solving 2x plus 5 times 0 is 11. This term is just gone. It's eliminated. We now are solving 2x equals 11. So x equals 11/2. So that means 11/2 would go here. And that's all three parts: slope, x-intercept, y-intercept. Kind of is just a tour rundown of the different things from looking into linear equations. And the really big tool that got us through that is the slope-intercept form. Y equals mx plus b. Gave us the slope and the y coordinate of the y-intercept. Any questions on the rundown for this one? Okay, next up is a distance formula. Really jumping around on this one, we went from chapter 3, linear equations, to now chapter 8, or excuse me, chapter 11, distance between points. We want to find the exact distance between these 2 points written as ordered pairs. We mentioned before when we were in chapter 11.1, you could just plot these, build a right triangle, use Pythagorean's theorem. That works each and every time. So say this is a real final exam question, you're allowed a 4-inch by 6-inch note card both sides. But if you didn't put this formula on the note card, but you have Pythagorean's theorem on the note card, that would be a good approach. If this formula is on the note card, really all it affords you is just a big shortcut. The shortcut, this is Pythagorean's theorem, but we've solved for the hypotenuse, which we're labeling as distance, says take x2 minus x1 squared plus y2 minus y1 squared, and that's how we'll compute the distance. So these are the x values, the x coordinates. These are the y values, the y coordinates. And that's really the whole punchline. We're finding the length of the legs and squaring them, as you would in Pythagorean's theorem. So substituting in this information, we'll get square root of. Now, another trick that's sometimes helpful just for seeing through all these different subscripts, x2, y2, x1, y1, is it doesn't hurt to also label these on paper on the real exam. Let's call this x1, y1, x2, y2. Then when we go to substitute in the information, it's just another helpful thing for our eyes to see where the information is pulling in. So go -5 minus this x1, -4. I think we mentioned before, this is kind of like doing the slope formula because we're operating on coordinates, but it's just a totally different formula on those coordinates. Now do it again for y2. It's going to be a +2 minus a -1. Being really careful with the double negation. That's the easiest way to make a mistake. So let's do the double negations first. We're treating this as a bona fide, pretty big order of operations problem. This is really -5 plus 4 squared. Plus, this is really 2 plus 1 squared. So on the next step, this becomes really -1 squared plus 3 squared. This is now just a bona fide 1 plus 9. So it's the square root of 10. And the instructions here are particular. I would probably just call that good. That looks good to me. That's a square root. It's in simplified form. Prime factors are 2 times 10, none repeated. But these instructions specifically asked us to round. So I don't think I would take off points if you left it in its exact form. But I bet the reason they're asking us to round is to see if we'll make this one particular mistake. Let me load up a calculator, forgot to do that. This is the mistake that's really easy to make in the calculator, which would cause a problem, cause us to lose points. We need a square root. And if you got to say this step, right where the red dot is, and put it in your calculator as negative 1 squared plus 3 squared, that's actually not correct, because order of operations in the calculator is done in an extremely literal way. Exponentiation happens first. 1 times 1, or 1 squared is 1. Negation happens second, because that's multiplication. So the calculator treated that as a negative 1. It's not square root 10 at all. Square root 10 comes out as 3.2 upon rounding. That's close, but a little bit off. So putting it in the calculator like this, with parentheses really capturing it, gives us the right numerical result. So I think that's what this problem is all about, asking us to put it in the calculator to round, is just to see if we accidentally make the mistake over here with forgetting parentheses. It comes out as 3.2 to the nearest 10. Well, that's the run through with the distance formula. The major reason we like the distance formula is because it gave us equations of circles. But now on to the next concept. Here, I believe we're back in chapter 1. This one is an absolute value equation. There'll be absolute value inequalities as well that could come up in this review. Solve 5 plus absolute value x minus 9 equals 11. This is a nice and rare hint, giving both solutions, reminding us that there will be 2 solutions to this. To solve something like this, we want to isolate absolute value first. So begin by subtracting 5. Absolute value of x minus 9 is then equal to 6. When absolute value is isolated, and only at this step, it can transfer into 2 different equations. This is why it says give both solutions. The change that happens is right here. We get, on the left version, x minus 9 equals negative 6. Or, on the version on the right, we get x minus 9 equals just positive 6. We took the absolute value of both of these versions of equations, we'd go back up to the original one. And that's because absolute value of negative 6, the right-hand side, just comes out as the positive 6 that we started with. So now these are solved in a really fast way. Add 9 to this one. X is going to be equal to positive 5. Or let me try again. Had a micro sleep on that. Add 9 to both sides. 9 minus 6 comes out as a positive 3. Add 9 to both sides on this one. This will be 6 plus 9, so x equals 15. So those are our both solutions. Well, any questions on this one here? Okay, it's kind of fun seeing these problems from way back in the day. Again, this was like week 1, maybe week 2. We were doing this kind of work. Felt like a lifetime ago sometimes after a 15-week semester like this one. So here's our next one to take a look into. This one, let's see, it says give an equation. It didn't say give a system of equations. So this one probably is something that we did in a chapter 7 application problem. We're told Mildred, interesting name, can row a boat 3 miles per hour in still water. On river, it takes her the same time to row 14 miles downstream as it does to row 7 miles upstream. We're already told x is the speed of a current. Give an equation that represents the problem. do not solve. So we're going to give an equation that represents how you would solve for the variable x, the speed of the current, but then we'll just stop once we get that equation. Let me move this to the next page just to make sure we have enough real estate on this one. Well, this one has two competing formulas. This is a uniform motion problem, so the main formula that we first saw was distance equals rate times time. But there's a big buzzword here, right where it said, let's use this highlighter. It takes sort of the same time to row 14 miles downstream as it does to row 7 miles upstream. That means the problem is more about time. So we can take the uniform motion formula and rewrite it as time equals distance divided by rate. So that's the equation that's going to match up with this particular information in the problem, that everything happens in the same amount of time. Next thing that's tricky is something happens when she goes downstream versus when Mildred goes upstream. So we've gone 14 miles downstream, 7 miles upstream. We have a formula that's going to organize time in both of these scenarios, upstream versus downstream. But to just help our brain organize all this information and actually get the right equation, let's write down a little bit more. So here is the downstream. Portion. Over here is going to be the upstream portion of information. Well, what do we know about downstream? Mildred rode 14 miles downstream. So distance equals 14 miles. Versus upstream, Mildred is an adventurous person. She went 7 miles upstream. Hopefully that's where she wanted to stop, and she's not trying to return to where she began. Maybe there's a little bit of drama in this problem when you think about it. So she stops rowing at 7 miles upstream. Hopefully there's no medical emergency happening of any kind. X is the speed of the current, but we also have that Mildred can row the boat 3 miles per hour in still water. We need to use this information somewhere. The speed of the current and how fast Mildred rows, that's the rate R in both of these pieces of information. So R is first going downstream, the speed that Mildred rows, 3. But because we're going downstream, the speed of the current X helps, so we go plus X. So these speeds are going to add up together. Mildred's now just flying down the river. But when we go upstream, the rate R that we indicated, it'll start with Mildred's rowing speed in still water. But because we're going upstream, Mildred's not going as fast. We subtract away the rate of speed of the current, which is X. We hope that X is not bigger than 3. The problem wouldn't make sense. But it could be close to 3. It could be something like 2.8 miles per hour. And that means it would take Mildred a long time to do the 7 miles upstream. But that brings us back to time finally. Time is distance divided by rate. We have distances, we have rates in both scenarios. So time is first equal to 14 divided by 3 plus X. So that's the times she spent rowing downstream. Upstream, time equals, same idea, take your distance. It was 7 miles per hour, divide by the rate of speed, which was 3 minus X. And now we have time broken down into the two different scenarios, going downstream versus going upstream. Here's where this buzzword of the problem connects back again. We're told Mildred it takes her the same amount of time to row 14 miles downstream as it does to 7 miles upstream. These are the two time values. So we can now just say, with a direct equality, 14 divided by 3 plus X is equal to 7 divided by 3 minus X. Both of these represent times, and setting them equal to each other says it takes the same amount of time to do the 14 miles downstream as it did to take the 7 miles upstream. The fact that we're dividing by the rates means it's a time value now. And this could be a question where the exam says, now solve it. You would probably use the cross product to clear out the denominator. But watch out for these words that will be in all bold, just as a reminder and a hint. This is a problem where we just needed the equation, and now we can move on to the next one. So here's the next one to take a look into. Now, this one's a pretty tricky one because it looks like it's more a vocabulary question than it is a legitimate math problem. I shouldn't say legitimate math problem. It is a legitimate one, but just kind of a strange one. It's a concept question more than anything. We're being asked how many ordered pairs solve the system. But you don't actually have to solve this to answer the question. We just look at what are the graphs of these two equations. How many ordered pairs solve the system shown? They mean the graph that's shown. These look like they're meant to be parallel lines. So that means there'll be no solution. Or you could just say none for how many. That's because the lines never intersect, and a point of intersection represents a solution. Follow-up question is, if there's no solution, is the system consistent or inconsistent? That's where the word inconsistent comes up. Inconsistent means no solution to your system of equations. So I would circle that part right there. Or you could just write down it's inconsistent. But you know, it's a timed exam, so circling the right output there is a pretty good strategy for this. The next tricky question is this system of equations dependent or independent? Well, there's only one way for a system of equations to be dependent. That's if they're coincident lines, in which case there would be a plot of just one line, maybe a note saying this one line represents both equations. So because there's two distinct lines that are being shown on the plot, that means it's not dependent. The system of equations is independent. It's a vocabulary question where lots of different things could happen on this one. So this is a good one to go back to. Chapter 4, Systems of Linear Equations. Section 4.1 is when we were first starting off, solving the system of equations. Let's put this here in the notes, just to put it in context for the exam review. Here are the other things that could happen for this kind of question. This is the one graph that gives us pretty much everything at once. The number of solutions, whether the system is consistent or inconsistent, and whether the equations are independent or dependent. So this is a good one to have available in the back of our mind, or maybe this is one that you put on your note card. Wouldn't be a bad choice, I'd say. Trying to bring these both together if possible. Let me see if I can just put it on the next page, actually. Okay, so the other things that could happen, like we mentioned, is if your lines intersect, they can intersect at a maximum 1 point. Then we would say here one solution. If this is the situation we have, that would mean it's consistent because there is a solution and we have independent equations. So the fact that we had inconsistent, that's actually the rare outcome. That only happens when you have parallel lines with different y-intercepts. If you have parallel lines with the same y-intercept, they are the coinciding lines or coincident lines. This is the only time the equations could be dependent. And in this case, there are going to be infinitely many solutions. So there's either one, none, or infinitely many. You can't have 3 solutions to a system of linear equations, which is interesting. But keep these graphics and definitions in mind. This is really what the question's all about. And there's lots of different versions of how problem 11 could come into play on the real exam based off these 3 different scenarios. But let's move on next to this topic. Looks like we were really skipping around now from this one. We went from chapter 4 to solving this kind of equation. This is back way over in chapter 9, quadratic equations. It's quadratic because the degree is 2. And when you think quadratic equations, you might think quadratic formula, which does work on this. You could expand this out, FOIL it out, move 11 to the opposite side to get to your 0, start finding A, B, C coefficients, compute the discriminant, put it all together in the quadratic formula. But you know that's not necessary this time. This is one of those times where having it in this format is a humongous upper hand. Right here where it says x minus 2 to the power of 2, this means the square has been completed. It's as if we're doing a completing the square problem, but someone did all the hard work, all the big setup in doing completing the square. What we now use in completing the square when we're at this stage is the square root method. We just straight out take the square root of both sides. But here's when big danger comes up. I mentioned we'll always emphasize this when it happens. If you square root an equation like this, and there's no assumption that the variable had to be positive or negative, you've introduced two different possibilities. Either we're going to get a positive square root of 11 or a negative square root of 11. So watch out for the plus or minus. Then the square root cancels with power 2 over here. You just get x minus 2 is positive or negative square root of 11. Add 2 to both sides. X is 2 plus or minus square root 11, and the whole problem is over. So if you did the quadratic formula, you're going to get the same exact value. It looks just like this, but it's painstaking. There's a lot of steps to show. It looks like it would simplify. Doesn't fit a fast concept question with no partial credit at 2 points. That's because this was all about the concept. It is fast. You just have to know the right tool in the toolkit. Don't forget the plus and minus. And that's a really, really rapid equation to solve. We talked more about it than actually solving it. Next one's also equation solving, but different from chapter 9, the quadratic formula, quadratic equations. This one we're about to solve, problem 13, is really just concepts about factoring. We solve stuff like this in chapter 6. The major tool in chapter 6 is to try to factor your equation with 0 on one side. But that's already been done. We have a full factorization for a degree 3 polynomial, 0 on one side. So the big idea on this one is use the 0 product property. The 0 product property tells us there is only one thing that can be an ultimate consequence if 3 things multiply and result in a 0. Either the first thing is 0, or the second thing is 0, or doesn't matter how many factors we have, if this is a complete factorization, we'll say, or the last factor, whatever it is, however many there are, is also 0. So this is the only way that equals 0 could potentially be true. One of these factors takes a value for x that places a 0 inside the factor. But now we have 3 linear equations, and we can solve these pretty quickly. On the first equation, -6 does the job. And even if you didn't write down the step in the middle, you can visualize it. Put a -6 there at the red dot, and you have 0 times a number. It absolutely would result in a 0. Likewise, on this one, the number that solves it is +5. This one you might want to be careful. It is 2 steps. Add 2, then divide by 3. But then the last solution is 2/3. So these problems, it's tempting to do a lot. Just like on problem 12, you could do a gigantic amount of algebra. You could expand all this out, FOIL everything together, get a degree 3 polynomial. But then after you did all that work, you're further away from solving the equation than you were at the very beginning on this one. Same idea with this one. It's in the right format to solve rapidly. Expanding out x minus 2, moving 11 to the other side to use the quadratic formula, that just takes you further and further away from the end answer, 2 plus or minus root 11, every time you take those kind of steps. So a big part of this exam is just pattern recognition. knowing what is the right tool based off what the equation looks like from the very beginning. Sometimes we'll need the quadratic formula or completing the square, but this was two examples of problems that go really fast if we know what's the major trick underlying it. Well, let's try out another one. So we went from chapter 6 to factoring now to simplify, and we're giving a cube root. Let's zoom in on that to really see the 3 there. So we're in chapter 8, dealing with roots and radicals. I like that it's a y power 6. That's kind of nice. That means the index of 3, it's just going to divide here, and we'll get a y squared out. The number 54 is the worst part about this. We need to factor this down. But 2 goes into 54 27 times, and 27 is a great number. That's 3 times 3 times 3. That's where you get the next perfect cube. So 54 can be factored nicely as 3 cubed times 2. So now let's take this whole problem and just rewrite it as cube root of 3 cubed times 2 times y to the power of 6. The things we can calculate, because the index is 3, are those two parts right there. Those will simplify. The thing that just stays right where it is that 2. So the reminder is the index divides the exponents. So right where it's 3 cubed, if we take the cube root of 3 cubed, we just get a 3. Likewise, with y power 6, the cube root of that is just y squared. We divide the index of 3 into the power of 6. We can check our answer because if you raise this to a power 3, y squared cubed causes the powers to multiply back to y power 6. If stuff left behind, we have the cube root of just 2, and that's our full simplification on this one. This one's tricky because it's surprisingly easy when you're doing the final exam to miss this one detail. It has to be a cube root on your final answer, or we could lose some points on this one. So make sure you still say cube root at the end. It's a good habit to just write it down on every single step, just to be hyper vigilant on that issue, and you'll be just fine on this problem. Okay, let's try out this next one. We're solving a formula, so that's way back in the day. That's all the way back in section 2.3, chapter 2 that we started the course with. We might have done a very similar problem on this one. When it says solve for the variable L, that should be italicized, but we'll forgive that. It just means get this L isolated on one side of the equation. And that's not too bad to do. We can start by subtracting 2w from both sides. P minus 2w equals 2L. Now to get L completely isolated, just divide both sides by 2. We'll have P minus 2w divide by 2. And I would just leave it in that form. There's no need to do additional algebra. Divide the right-hand side by 2, and now it's just L. The whole problem is done right at that step. So you don't have to do anything further. That's where the problem will end. Well, now on to problem number 16. For this one, we're back in chapter 8, roots and radicals. But we're in a specific section. We're on simplifying rational exponents, section 8.3. This is where we start to review exponent laws for a second time. So we'll do a couple problems along those lines to see how they go. It says evaluate if possible. You know, that if possible statement is kind of worrying. So a second version of this problem could look like this. Let's call this number 16, version 2. Here's what an impossible problem might have looked like. Negative 125 to the power of, so let me make it be something slightly different. How about negative 25 to the power of, I don't want a negative 2/3. Let's make it be, how about a negative 3/2. Let's go with just a positive 3/2 to really isolate the issue. So for this one, we would say, if the instructions are evaluated, if possible, we'll say not possible. as a real number. The reason for that is the negative sign here with the division by 2 tells us this whole thing is not a real number whatsoever. We could write it in as a complex number, but for these kind of problems, we're going for just real numbers for these expressions. Since we never learned how to raise something, well, we did raise some numbers to power 3, but this one looks like it's possible because the denominator, which becomes the index of a root, is 3. So we don't have an issue like we do over here. This one turns into a square root of a negative number. So this one, working it out in steps, goes like this. 125 to the power of negative 2/3 turns into this structure. The major thing to watch out for is the 3 right there. The denominator for the rational exponent becomes the index to the root we're taking. The negative 2 just becomes the outer exponent. The number on the inside is 125. And we can compute that. If we did the same thing over here, we'd have the square root of negative 25, which is the not a real number portion. So this turns into cube root of 125 is just 5. Now raised to the power negative 2. Well, the exponent law for this, power raised to a negative 2, means you drop 5 to the denominator with a positive exponent. So the negative 2 became a positive 2. Now we can square the denominator. We get 1/25 altogether, solving this problem. So the formula, or the idea, the big idea we used, is that that denominator there became the index for the root. We could have put the power 2 on the inside, but it was just convenient for this problem with a numerical value to put the power negative 2 on the outside. This one will do a little bit different. We want to change this thing that's in exponent form into an equivalent expression in radical notation. So we need some kind of root in this problem. It's kind of like what we did here, but just doing it in a different way. So let's take 7x cubed to the power of 2/5. The similar part is that denominator tells us we're dealing with a 5th root. The thing that's similar, the reason we're doing this in a slightly similar way, is for this particular problem, it's more convenient to put the power of 2 on the inside like this rather than the outside. So this becomes a 5th root. That part will never change. The denominator is telling you the index of the root to use in both cases. But there's some flexibility with the numerator. Power 2 can either be on the inside or on the outside. It's convenient here because no one wants to take 125, square it, or raise it to a power negative 2, and then take the cube root. It's fast to just take the cube root of this small number right as we see it. But over here, with these things, it's a little bit easier to simplify if we go 7x cubed and then square on the inside, finalizing our answer. So the equivalent expression in radical notation, we have radical notation the moment we write in this 5th root here, so that's what that's referring to, is just square what's on the inside. 7 squared for 49. X cubed squared will give us x to the power 6. Then we just stop. The keen-eyed observers among you might notice, hey, this simplifies, not because of the 49, but the power here, power 6, is higher than the index of 5. So some people might simplify this one, but that wasn't what this problem was all about. It was really just a conversion problem into radical notation. So even if it does simplify, this is a really good stopping point right here. Well, we're just about out of time. I think we have enough time to do one more problem. So let's take a look into solving problem 18. Then when we come back on Thursday's class, we'll just move through the rest. It looks like we got a little bit more than halfway through. So we should be on good pace for completing this entire document on Thursday. It's another square root problem. So we're still out here in the land of chapter 8, roots and radicals. We want to simplify this where two roots are being multiplied against each other. But you know, the big deal that we made about this problem the last time we saw something like this is sometimes what you want to do is not treat them as separate pieces, but bring them together. So root 20 x squared y times root 8 x power 6 y squared can be solved even faster if we go like this. Multiply h times 20 to get a 160. X power 6 times x squared gives us x to the power of 8. And y times y squared gives us y cubed. But you know what? That's better as y times y squared because the index here for the square root is 2. X power 8 is a perfect square, so it's y power 2. But 160 isn't. But you know, that one factors pretty fast as 16 times 10. 4 times 4 is 16, so that's the perfect square. 10 contains factors just 2 and 5, so it can't reduce. X power 8 will reduce. Y is another one that cannot reduce, but y squared will. So green are the things that are going to move, the things that are perfect squares that we can take the square root of. We're assuming the variables represent positive real numbers, so we won't have absolute values in this problem. The 10 of the y is the stuff we can't do anything at all with. So the question ends like this. Take the square root of 16 for a 4. Square root of x power 8 means the index, which is 2, divides that power. We get just x power 4, much like with the cube root. Likewise, this becomes just y to power 1, just a y. And we're left with the square root of the stuff we could have never done anything with in the beginning, just a 10y. Well, we did it, folks. This is one way to do the problem. But the word of warning is, when it says simplify, you might have read this as a different problem. You might have simplified this root here, then simplified this root here independently of the first one. You still have to multiply them together. And when you do that multiplication of those two things together, you're going to get another root that has stuff inside of it that still simplifies, which is kind of a painful realization. So this problem can be like a problem that's 3 times as long as what we just did if we treat these as independent pieces. But you know, the moment you use properties of square roots and put them together and work with what you have on the inside, it makes a problem a lot nicer. In fact, we've already done that once in the notes. Way up here on the top, it was the same kind of deal. Rationalizing this one, root 15 over root 35, might have meant to you multiply by root 35 over root 35, and you would get to this, but it's a lot more work. The moment we put them together, take the divisions of roots and divide on the inside to simplify on the inside, the whole problem became just a lot more approachable. And that's the same story as what we are seeing on this one down below here. Well, we'll make this our stopping point. When we come back on Thursday's class, we'll just be moving through the rest. Have a great night, folks. We'll talk soon on Thursday's class.